There is a cold wound in the oldest light we can see, not a lens artifact, not instrument noise, a real measurable temperature deficit, approximately 70 millionths of a degree below the surrounding average, embedded in the cosmic microwave background. The relic radiation released roughly 380,000 years after the Big Bang. Every photon in that signal carries a frozen record of conditions when the universe was less than 100,000th of its current age. ESA scientists processed that record for years. The standard cosmological model, lambda CDM, fit the data with extraordinary precision, almost everywhere. The cold spot sits at galactic coordinates L approximately 209 degrees, B approximately minus 57 degrees. It spans roughly 5 degrees across, 10 times the apparent width of the full moon. At those angular scales, the CMB temperature signal runs approximately 10% weaker than the model predicts. Planck's legacy data release confirmed it had survived every instrument check, every reprocessing pass, every attempt to assign it to a hardware fault. The anomaly was not noise. It held its position, held its temperature, held its shape across independent datasets. The official explanation arrived in 2015. Using WISE 2 mass and Pan-STARRS 1 surveys, astronomer Zapputi and colleagues mapped the galaxy distribution in that direction and found a supervoid, a region of unusually low cosmic density, roughly 220 megaparsecs in radius, centered at redshift Z approximately 0.22. Photons crossing such a void lose energy through the integrated Sachs-Wolf effect. A cold imprint on the CMB follows naturally. The case appeared manageable, but the supervoid is itself a statistical anomaly. In standard lambda CDM simulations, a structure of that size and emptiness registers as approximately a 3.3 sigma fluctuation. The explanation for one rare feature required another rare feature, nearly as improbable, aligned in the same direction, at the right redshift, with the right radius. Science did not declare a crisis. It revised estimates, scheduled further surveys, updated the working answer. The cold spot remained on the table. Behind both anomalies, a theoretical framework had already reframed the question. Alan Guth described inflation not as a single, cleanly concluded event, but as a self-reproducing process. A vast background expansion from which local pockets periodically break off, cool and condense into separate universes. Our Big Bang may have been one such ignition, one bubble in a potentially unbounded foam, each pocket carrying its own physical constants, its own relic light, its own thermal history. In that geometry, the measure problem alone, how to assign meaningful probability when the sample may be infinite, has no resolution that satisfies the field. If such a geometry is real, another bubble could have pressed against ours in the earliest moments of our existence. The collision would leave a mark in the oldest light. The cold spot would not be a statistical footnote. It would be the oldest bruise in our sky. The process that produced our universe did not stop with our universe. In regions where the inflaton field drops below a critical threshold, local expansion ends. Space cools. Matter condenses. Physics locks into the constants that define everything a civilization can eventually measure. But surrounding that pocket, the larger inflationary background continues expanding, faster than any signal could cross it, generating new pockets, new ignitions, each sealed from the others not by distance but by geometry. This is not a speculative addition to the model. It follows from the mathematics when the equations are taken without modification. The process populates a structure theorists call a multiverse of pocket universes as a structural outcome, not a metaphor. Each pocket begins with its own thermal history. Each one carries its own relic light, its own frozen record of early conditions. In work published in Physical Review D in 2025 and 2026, Kai, Zhang, and Guan examined what a physical collision between two such bubbles would actually leave behind. Not a simple cold patch in the sky. Their models pointed to remote quadrupole and remote dipole fields, patterns encoded in how the CMB would appear from distant points along our past light cone, rather than from our position alone. They calculated these fields could improve constraints on collision parameters by roughly an order of magnitude compared to earlier approaches. The signature, if it exists, does not announce itself. It is geometrically specific, statistically narrow, and embedded in data that requires survey instruments not yet fully operational. Absence of confirmed detection is not resolution. It is a measurement problem, and the measurement tools are still being assembled. Then the scale changes entirely. Hugh Everett was a graduate student at Princeton in 1957 when he submitted his relative state formulation of quantum mechanics. His interpretation required no collapse of the wave function during measurement. It allowed the wave function to continue evolving unitarily, with all outcomes coexisting as branching states. The observer does not cause a collapse. The observer becomes entangled with one branch while the others persist, separated, inaccessible, but not erased from the formalism. The physics community received the paper politely, then largely set it aside for 2 decades. What Everett described carries a consequence that resists easy absorption. If every quantum interaction generates branches, and those branches are real in any meaningful sense, then the universe experienced at any given moment is not the universe. It is one weighted path through a space of parallel histories, all of which the same equations treat as equally valid solutions. The Stanford Encyclopedia of Philosophy notes that in this interpretation, multiple worlds exist in parallel in the same space and time, separated not by distance but by decoherence, a process so complete it functions as a boundary no signal crosses back from. It does not add new physics. It removes the postulate of collapse and follows what remains. The mathematics does not prohibit this picture. The discomfort is not with the equations. It is with what the equations taken literally require the word real to mean, and whether that meaning has ever been as stable as it appeared. If every quantum outcome exists as a real branch, a specific consequence follows, one that most physicists reject not because the math forbids it, but because it misreads what the math says. The argument runs like this. In any situation where survival is physically possible, even with vanishing probability, a branch exists in which the observer continues. If branches are real and consciousness persists along whichever path remains coherent, then no observer ever experiences their own termination. They always find themselves in the branch where something, however improbable, allowed continuity. Jacques Mallat, writing in 2009, named this quantum immortality and identified it as an extension of what he called the quantum suicide fallacy. The core error is not philosophical, it is mathematical. A branch with near-zero amplitude does not carry the same weight as a branch with high probability. Treating all branches as equally inhabited by a surviving observer ignores the measure, the relative density of outcomes, that the formalism actually assigns. The surviving branch may exist. It does not follow that existence is the same as experience, or that experience is independent of amplitude. What remains after the argument collapses is not reassurance. It is a more uncomfortable residue. The formalism of quantum mechanics, in its most literal reading, does not contain a clean definition of personal identity across branches. The word I survives in the equations only as an entangled state. What that entangled state means for continuity has no settled answer. The second problem is physical. It has mass. Roughly 27% of the energy content of the universe consists of dark matter. Visible matter, stars, gas, dust, planets, everything detectable across the electromagnetic spectrum, accounts for approximately 5%. The remainder does not emit, absorb, or scatter light. It is known through gravitational effects alone. The rotation curves of galaxies, the bending of light around clusters, the large-scale structure of the cosmic web. In models proposed by R.N. Mohapatra and others, this invisible component may not be a single unknown particle. It may be an entire mirror sector, a duplicate set of particles and forces related to ours by a discrete symmetry, interacting with our sector almost exclusively through gravity. A mirror photon that does not couple to our electromagnetic field. Mirror baryons that form structures according to their own chemistry. a parallel physical infrastructure gravitationally present, electromagnetically absent. The model carries a specific constraint. A mirror world with the same temperature history as ours would alter the abundances of helium, deuterium, and lithium produced in the first minutes after the Big Bang. To remain consistent with observations, the mirror sector must be colder. Mohapatra notes that under such conditions, the mirror world would consist predominantly of mirror helium, with very little mirror hydrogen, a dark sector built from different proportions than our own, by the same rules toward a different composition, not a reflection. A colder, heavier, invisible twin, occupying the same space, never touching our light. A free neutron outside an atomic nucleus does not last long. It decays. One down quark flips to an up quark, releasing an electron and an antineutrino, leaving behind a proton. This process, beta decay, is one of the most precisely studied transitions in all of particle physics. Physicists have been measuring how long it takes for decades. They cannot agree on the answer. Two experimental methods exist. The first, the beam method, directs a slow neutron beam through a detector and counts the protons that appear as neutrons decay. It measures how many products are created. The second method, the bottle approach, traps ultra-cold neutrons in a magnetic or material container and counts how many remain after a fixed interval. It measures how many neutrons disappear. By standard physics, both measurements must converge. A neutron that decays produces a proton. Counting protons produced and counting neutrons lost should give identical decay rates. They do not. The bottle method yields a neutron lifetime of approximately 879.4 seconds, plus or minus less than a second. The beam method yields approximately 888.0 seconds, plus or minus about 2 seconds. The gap between them is roughly 8.6 seconds, a difference of over 4 standard deviations. In precision physics, at this level of experimental refinement, 4 sigma is not a rounding problem. It is a structural question. The conservative answer is systematic error, some unidentified bias in one or both experimental setups, neutron losses through gaps in the bottle walls, beam flux miscalibration, detector inefficiencies, could account for the discrepancy without requiring new physics. Wietfeld, reviewing the anomaly in 2024, identified this as the most probable resolution, while explicitly noting that new physics could not be ruled out and that the problem remains open. The less conservative answer follows directly from the mirror matter framework. If a small fraction of neutrons, approximately 1%, oscillate into mirror neutrons before decaying, they vanish from the bottle without producing visible beta decay products. The bottle method would count them as gone. The beam method would find no corresponding proton. The books would not balance by exactly the amount observed. Bereziani, writing in 2019, calculated that a mass splitting between neutron and mirror neutron of approximately 10 to the negative 7 electron volts, combined with magnetic fields of several Tesla, could drive this resonant transition at the rate required to explain the discrepancy. The hypothesis was tested. A team led by Broussard at Oak Ridge National Laboratory built an experiment at the spallation neutron source, applying a 6.6 Tesla magnetic field to a cold neutron beam and searching for the regeneration signal a mirror neutron transition would produce. The result, published in Physical Review Letters in 2022, excluded the specific parametric scenario Bereziani had modeled, the one calibrated against a 4.6 Tesla NIST beam measurement. That particular door was closed. The discrepancy remained. The neutron lifetime feeds directly into standard Big Bang nucleosynthesis calculations. The predicted abundances of helium, deuterium, and lithium formed in the first 3 minutes of the universe. A neutron that lives longer affects how many survive long enough to be captured into nuclei. The anomaly is not isolated to laboratory physics. It touches the oldest chemistry in existence. What the detectors at Oak Ridge measured was the absence of something. No mirror regeneration at that field strength, at that energy under those conditions. A different mass splitting, a different coupling, a different magnetic environment. These remain unconstrained. The specific model failed. The gap in the seconds did not close. The question of a mirror sector does not stop at particles. It scales. In 2018, cosmologists Latham Boyle, Kieran Finn, and Neil Turok published a model in which the universe is not simply old, vast, and singular. In their framework, the Big Bang is not the absolute beginning of everything. It is a boundary point, a moment of symmetry between two halves of a single system. On one side of that boundary, our universe, expanding forward in time. On the other side, a CPT mirror image expanding backward in time composed of antimatter with spatial coordinates reflected. The two halves together form a structure that is globally symmetric under the combined operation of charge conjugation, parity inversion, and time reversal. The model does not invoke new forces or exotic mechanisms. It asks what happens when the standard equations of physics are applied at the level of the entire universe rather than within it. The answer it produces is a cosmos that comes in pairs, not as parallel branches or neighboring bubbles, but as a single object with two temporal directions meeting at a point. The predictions are specific. Neutrinos must be Majorana particles. The lightest neutrino must be massless. Primordial gravitational waves at long wavelengths must not appear in the CMB polarization signal. The model also proposes a dark matter candidate with a mass of approximately 4.8 times 10 to the 8th giga-electron-volts, a sterile neutrino-like particle produced at the Big Bang boundary by the same symmetry that defines the mirror structure. These are testable constraints. Several are already being pressed by current and planned experiments. None have yet eliminated the model. The discomfort is not in the mathematics. It is in what the model requires you to accept about directionality. Time in this picture is not a universal arrow pointing from past to future. It is a local property of each half of a symmetric system. Our sense that time flows forward is not a feature of physics. It is a feature of our position. The geometry extends further. In brain-world models, our three-dimensional universe is not all of space. It is a membrane, a brain, embedded in a higher dimensional bulk. Other brains may exist in that bulk, separated not by conventional distance but by displacement through dimensions we cannot directly measure or traverse. The forces that define our matter, our light, our chemistry are confined to our brain. Gravity is not. It propagates through the bulk, which means a neighboring brain could exert gravitational influence on our own structure while remaining entirely invisible to every instrument we have built. André Kuntz and Andreas Trautner examined a five-dimensional brain-world geometry in which the fifth dimension is compactified on a circle. The model produces a characteristic warp factor, a hyperbolic distortion of the geometry between brains, that leaves potential imprints on the gravitational wave spectrum and on precision measurements of forces at short distances. No neighboring brain has been detected. No deviation from standard gravitational behavior at testable scales has been confirmed. But the experimental bounds that would definitively close this scenario require measurements at length scales and sensitivities that remain out of reach. An invisible surface, separated from ours by a dimension we cannot enter, pulling on us through the only force that does not stop at boundaries. This is not a metaphor. It is the formal consequence of taking the geometry seriously. At the center of a black hole, the equations stop working. This is not a rhetorical statement. General relativity, which correctly describes the behavior of massive objects across billions of light years, produces a singularity at that point. A location where density becomes formally infinite and the mathematical description breaks down. Physics as currently formulated does not say what happens there. It says the tools no longer apply. One answer, developed by Lee Smolin and others, treats this failure not as a boundary but as a transition. In this framework, the interior of a black hole does not terminate in a singularity. It gives rise to a new region of space-time, causally disconnected from the universe that produced it, expanding according to its own initial conditions, inaccessible to any signal moving outward through the event horizon. A universe inside a universe, not metaphorically, as a consequence of the geometry. Smolin extended the idea further. If the physical constants of a daughter universe are slightly varied from those of its parent, the way biological offspring carry mutations, and if universes that produce more black holes also produce more offspring, then the population of universes would evolve over cosmic timescales toward configurations that maximize black hole formation. Our universe is extraordinarily efficient at forming black holes. Under this model, that efficiency is not coincidence. It is inheritance. The model makes specific, falsifiable predictions about the range of physical constants compatible with high black hole production. Some of those predictions have been tested. None have yet decisively eliminated it. None have confirmed it either. What all 10 mechanisms in this account share is a single structural feature. None of them require the parallel structure to be elsewhere. The CPT mirror is not across the galaxy. It is on the other side of the moment of our origin. The neighboring brain is not in another dimension in the science fiction sense. It is displaced through geometry that begins where our measurable space ends. The mirror neutron does not travel to another universe. It oscillates locally within the same laboratory, within the same magnetic field, within the same experimental apparatus that has been measuring it for 40 years. The cold spot is not a window, it is a temperature reading, 70 millionths of a degree below the surrounding average in the oldest light we can observe, at coordinates that have survived every instrument check run against them. These are not stories, they are data points, theoretical frameworks, and unresolved discrepancies, the kind that accumulate in the literature without resolution, that appear in the appendices of precision measurements, that survive peer review without confirmation and without dismissal. Science does not close them with a declaration. It assigns them error bars and schedules them for the next generation of instruments. The gap in the neutron lifetime is still approximately 8 seconds wide. The cold spot is still cold. The equations at the center of a black hole still do not resolve. And somewhere in the bulk, if the geometry is real, a surface exists that has no light, no signal, no name. Only gravity pulling quietly through every dimension we have no way to enter.